Hello everyone. In the coming set of lectures, we are going to focus on the frequency domain methods in designing the controllers. Indeed, we first will start with analyzing the systems in the frequency domain using the body plots, and then at some point we will start to design the controllers. In the first lecture, we will indeed deal with the general concepts, and we'll see how the steady state errors for the closed loop system could be related to the body plots. So again, we are going to use the body diagrams. Okay, so this is an important fact to keep in mind. We will use the body diagrams for controller synthesis later, but before that we will do some analysis. If you don't remember how to draw body diagrams for a given system, it would be nice if you just try it out and practice doing it for a given number of systems. So you need this knowledge in the upcoming lectures. So what we are going to study is an alternative to the use of root locus. Right now we know how to analyze the systems using the root locus approach and how to design the controllers using the root locus. But now we will analyze and then synthesize a controller for a size-so linear system using the frequency domain methods, which are based on the body diagrams. First, we will focus on some basic analysis concepts, and then we'll move to the controller synthesis. In the coming slides, we will see how the loop transfer function LOS, which is the multiplication of GC and GP, can be useful in order to describe the behavior of the closed loop system. So we will consider the loop transfer function LOS, and we will describe the behavior of the closed loop system. And then later we will see if we want to have a desirable closed loop behavior, we can kind of change the loop transfer function in a desired way. So basically we see how to understand if a closed loop system is bistable only by looking at the L of S. So if we have the body plot for L of j omega or L of S, looking at the body plot or using some other frequency methods that we will consider later, we will determine whether the closed loop system is bistable or not. If it's not stable, we might try to change L of S in order to make the system stable. We will also see what characteristics of T and S, the closed loop transfer function and the sensitivity function, can be inferred from L of S, the loop transfer function. And we will see how we can deal with the disturbance rejection for the closed loop system using L of S. We will also see how to relate the characteristics of the body diagram of L of S to the time domain specifications, such as the rise time, settling time, overshoot, and so on and so forth of the step response for the system. At this point, we will be done with the analysis of the system using the frequency method, and then we'll be ready to start synthesizing the controllers. Alright, so as the first step, let's have a look on how we can determine the steady state error for a given system by looking at the body diagram of L of S. The steady state error will be for the closed loop system. And we will have the body diagram of the loop transfer function or L of S. Okay, so if you look at this table that we have over here, you should remember that the steady state error for the closed loop system could be obtained by checking the type of the system at first place. So you should remember that we have no pole at the origin for the type 0, no pole at origin. For type 1, we have one pole at the origin. For type 2, we have two poles at the origin for the system. Basically, the number of the poles at the origin will determine the type of the system. And then based on the type, we can find the finite values for the error constants, Kp, Kv, or Ka. And once we have those static error constants, which will be either a finite value, 0, or infinity, we can determine the steady state error. For the type 0, for the step input, it will be equal to 1 over 1 plus Kp. We will have infinity for the ramp and parabola inputs. For type 1, we will have 0 for the step reference input, 1 over Kv for the ramp, and infinity for parabola. And for type 2, we will have 0 for step and ramp inputs, and 1 over Ka for the parabola input. On the other hand, we know that Kp is the limit of L of S as S goes towards 0. Kv is equal to limit of S times L of S as S goes towards 0. And Ka is equal to limit of S squared times L of S as S goes towards 0. So this information we already have as well. Now we want to see how we can determine these Kp, Kv, and Ka, and as a result we have an idea for the steady state error using the body plot of L of S. The important fact here is that you can see that Kp, Kv, and Ka are determined as S goes towards 0. Okay, so this is important to remember. When we draw the body plot for the system, we will replace S with j omega, and limit of S going towards 0 will be equivalent to limit of omega going to the 0. So we will consider the part of the body plot at very low frequencies. For L of S, in general, we will consider it in the body form. So we will have L tilde, which is the generalized gain, over S to the power of h, where h determines the type of the system, times first order zeros. Let me write j omega tau I over first order poles 1 plus j omega tau j times second order zeros and poles. So indeed we will have a set of them, product of the second order poles in the form of 1 plus j omega ai plus j omega squared bi. We can show them in this form, yeah, indeed. And for the second order poles, we can have them in the form of 1 plus j omega aj plus j omega squared bj. Since once indeed we have the L of j omega, let me replace all the s that we have with j omega. Okay, it takes some time for my system to catch up, but you can think that we have L of j omega equal to L tilde over j omega to the power of h times the first order poles and zeros times the second order poles and zeros. Now, if you want to find out the limit of L of j omega, as omega goes towards 0, we will end up with L tilde over j omega to the power of h, because for the rest we will have a multiplication of 1s over 1s for the first order and second order poles and zeros. So these are products. Yeah? And this will be equal to L tilde over J omega to the power of H. Now, if H is equal to 0, we will have a 0 type or type 0 system. And the limit that we have, limit of L of J omega as omega goes towards 0 will be equal to L tilde, which is equal to Kp. So for a type 0 system, on the other hand, you should know that in terms of the body plot, at the low frequencies, we will have a 0 dB per decade. L of J omega. So at low frequencies, we will have 0 dB per decade. And the value that we have over here, the amplitude that we have here, will determine us the Kp. The error constant. You can also see it over here, yeah? So L tilde in this example is equal to 20 decibel, which is over here. So we have 20 dB, and it's equal to indeed 10. And as a result, for this system with the body plot for L of J omega, we will have the steady state error for the step reference equal to 1 over 1 plus Kp, which is 10, and it will be equal to 1 over 11. So in this way, just by looking at the body plot of L of S or L of J omega, we can determine the steady state error for the type 0 systems quite easily. For the type 1 systems, we will have H equal to 1 for type 1 systems. Limit of L of J omega as omega goes towards 0 will be equal to L tilde over J omega, and in terms of amplitude of J omega as omega goes towards 0, we will have L tilde over omega. And again, keep in mind that this happens for the low frequency parts. Since we have a type 1 system, we know that L tilde is indeed equal to Kv, and it's equal to limit of S L of S as S goes towards 0. Okay? So we are now interested in finding L tilde in order to find out or obtain the value for Kv. In low frequencies, we have the amplitude equal to L tilde over omega. So if we kind of be able to replace omega with 1, then we will have amplitude of L of J omega at the low frequencies, or as omega goes to 1 or it's equal to 1, will be equal to L tilde, which is equal to Kv. So we need to focus on the low frequency part. You can see it over here. And since we have a type 1 system, we know that at low frequencies we will have minus 20 dB per decade as the slope. We need to extend that line and find out the value at omega equal to 1. If omega equal to 1 is not indeed included in the type of the drawing that we have for the very low frequencies, we extend that and end up with the value for the Kp, where omega is equal to 1. And then we will have that value. For this example, it's equal to 20 decibels. So Kv is equal to 20 decibels. For this example, Kv is equal to 20 dB or it's equal to 10. So this is an example. Yep, we might had an example in which I can change maybe the x-axis 10, 100, 0.1. This could be a second example. We can see that omega equal to 1 in this example lies in the first part of the body plot, and as a result we can just directly find out the value of amplitude of L of j omega at omega equal to 1. This time will give us the kV, which is equal to 40 dB or 100. Okay, so for the second example that we had, kV will be equal to 40 dB or it will be equal to 100. It just depends on whether omega equal to 1 lies or is included in the first part of the body plot or not, where we have the slope of minus 20 dB per decade. Similarly, for a type 2 system, we have for type 2, we have the amplitude of limit of L of j omega as omega goes towards 0 will be equal to this limit L tilde over j omega squared. The other terms will be replaced by 1 and as omega goes towards 0, and it will be equal to L tilde over omega squared. At very low frequencies, we will have minus 40 dB per decade line. So here we will have the slope equal to minus 40 dB per decade. And similar to what we had for kV, in this case we can find out Ka, which is equal to L tilde. And we can find out this by finding or replacing omega with 1. Let's say this is the example that we have. If omega equal to 1 is here, we would need to extend what we have here for the initial part of the body plot and then obtain the value for Ka. If, as another example, omega equal to 1 was here, this is the second example, then we could find out the value for Ka from without extending the first part of the body plot. Yeah, in omega equal to 1 is included in that part. So this is indeed how we can determine the value for the error constants, and as a result we can determine the steady state error. If we are, later we will see, if we are satisfied with the steady state error, we don't need to change that part of the body plot. But if we are not, we might need to move the body plot in the low frequency segment up or down, or change the slope of the body plot, which means that we change the type of the system. We'll come back to this later when we start to synthesize the controllers. Alright, so for this lecture I think we are done. In the next lecture we will continue analyzing the systems in the frequency domain. Thank you for watching and see you in the next video.